operation of a flash bulb and a digital camera. The camera is powered by a battery consisting of two 1.5 volt cells connected in series.
Okay.
Define electrical capacitance.
Oh, so the first one is define capacitance. I think we did that in the last question, didn't we? Yeah. You know, capacitance, the ability to hold charge, where 1 farad of capacitance is 1 coulomb held per 1 volt potential difference. So I think that's okay. B?
Calculate the charge stored and the capacitor is fully charged.
Okay, so we charge up the capacitor and we want the charge?
Yes.
So that's easy. That's just Q equals CV for babies. 1,680 millicoulombs. Is that right? Yeah? We all got this? Okay, what's next?
When a photograph is taken using the flash, the fully charged capacitor discharges to a potential difference of 0.4 volts in a time of 0.038 seconds.
0.038 seconds, okay?
Calculate the loss of energy from the capacitor during the discharge.
Interesting. No, the first thing that I was thinking when I heard this just now is, do we actually need to know the time? They want the energy. So that's a half, well yeah, but also it's a half QV. Some of the question? So we will need the time for the second half, okay. But for the first half, not necessarily. Because we can just do a half CV squared, right? So that's 0.5 times 560 times 10 to the minus 3 times 0.4 squared. What's that, please? Yeah.
Are we supposed to use the 0 because it dropped from 3 to 0?
Oh, it dropped by 0.4, not it dropped to 0.4. Oh yeah, no, I'm not finished. Once I get the answer here, I'm going to take it away from what the total would be. I suppose so. It would make me feel better not to. This here has a value, and so then the change in the work will be the total originally, which is a half C V squared minus this one, a half, and that one, and then V squared. But as you pointed out, Monica, you know, well, what did you use for your voltage? Did you use 8.6? Oh, you did 3 minus 0.4, 2.6. I don't know if you'll get the same answer. My only concern is because the voltage is being squared. It will be the same as this? Well, let's see. Can someone hit this in on the calculator? Basically, it's going to be 250, 280? 0.2. 0. The total?
No.
No, you can give me what you have.
So the 0.79, 0.8.
0.8 is the total here.
Yeah.
Did you get this, Monica? You see, oh, dude, just type it in. KJ, can you type this in on the calculator, please?
The first one is 2.52 and the second one is 0.045.
2.52 and the second one is
0.04.
5.
It's gonna be 2 point something.
Yeah. Dude, you have calculators. Just type the blooming thing in on the calculator.
2.47.
Oh,
Five
that's
to six.
That's significant. 2.47.
5 to
52, so 2.48 joules. Okay. Porridge. It's the square. It's only because the voltage. It's how the square of the voltage changes, not the voltage change. If this formula was just a V, then it's fine. What you did would be right. No, if you did instead, you basically did this. You said that is equal to 3 minus 0.4, that's equal to 2.6, and if we use this, we can get the change, the loss in the work. But the formula doesn't contain V, it contains V squared. So what you should be doing instead is saying, the square of the voltage changes like this. So if I use that in my formula, I'll get the same answer. Okay, what's the next part here?
determine the average power delivered by the capacitor.
Okay, so that's kind of like a question I made up in the worksheet, isn't it? The power. So that's nice. We worked out how much energy was released, and we have the time because they said it to us. It's 0.038. So it really is just this, is it?
Yeah.
What's that, so? 65.3 watts. Yeah?
Yeah.
Okay. Next? Or is that the end of the question? That must be the end, is it? Is there more? Are you not talking to me anymore? Did I offend you in some way? Is there more to the question, or is that the end?
Yeah.
That's the end, okay.
How do you get P? P equals over T.
Thank you. What?
This is so cold, teacher. Teacher, I should say that we don't have exam in this class. Next week.
I think where you sent your timetable? Yes. Is it about this? I mean, can I close this? Yeah.
When we find the total energy, we subtract 2.52 minus 0.045. But if it's a minus, it has to be exact like 2.475 because you just said the 2.
Yeah, really in my calculations I should use 4 significant figures and present my answers to 3.
Yeah, but I mean, if it's like multiply with it, divide, you have to like, but if it's like plus or minus, it has to be exact. So.
Well.
Because if we use 2.475, the answer will be 60.13. So it's gonna be the 65 or.
It's a bit hard for me because I don't have my calculator open, but what really usually happens in the exam is you have, like for example, I wrote down 2.48, okay? But really what's going to happen if I was doing this myself in the exam is I would still have that number on the screen because it was the last thing I got. And I should use this number in the next calculation as an example. So where possible, you should try and use the number that's still on the calculator when possible. If not possible, then you should use 4 significant figures or more and present your answer to 3. As long as you do that, you'll get the full marks because you didn't do anything wrong. You know, if you're doing this or more in calculations and then present the answer to 3, then you get the mark, even if it's a tiny bit different to someone else in the class. In real life though, like I said, this number is still on the screen and so you can carry it into the next part. And I kind of think they expect the students to do that. You know, if this part said what is the work and the screen said 4.70216 blah blah blah, and the next part all you had to do was divide that by the time, then they kind of expect this to be divided because it's still on the calculator screen, and so this should be more exact. Yeah. Can we close this now?
No.
What's wrong?
What if you use P equal to V squared over R and by using 5 time constant equal to 5 R3
P equals, go on, yeah, go on, P equals V squared
over R.
over R. Ah!
So I get different.
Excellent question. Yes, you'll get the wrong answer,
Yeah.
but why the heck is it wrong?
Yeah.
Free porridge for anybody who can tell me.
Really?
Maybe. I know I can't give you hints if there's a free porridge.
P equal R.
Is that an answer, or are you just telling me something?
P equal RC then find
My porridge is still safe.
5.
That's, where's the verb in that sentence? What are you telling me? What are you telling me?
To find the R.
Okay. But I think that's what he did to find the or, was it? How did you get the or?
5 time constant.
Yeah, so he already did that, and he got the wrong answer. So, anyone else? Go on. Yeah. Yeah. What about the V? Yes. Good. So we must use. I thought you were going to get a porridge. Yeah. No. No. Let me tell you. Stop. The problem is, Lee, that these formulas, they work and they're fine. But you've got to remember, true, this is not really changing, but this is changing. In fact, because it's a capacitor, the voltage is discharging. Now, you might say, well, hang on, wasn't that always true? Why has it not been a problem so far? Well, because if you did want to use this, you would have to use the average voltage. Like you couldn't use, I thought Monica was going to get it there. You can't use the tree because that's the voltage at the beginning, and if you did that you would be saying the power is too high. You can't use the voltage at the end after the 0.038 seconds because that would be too low. And you can kind of use the voltage in the middle, but that technically isn't right because this graph is not a straight line. If it was a straight line, you could use the middle value. But I would be curious to see how close we would be if we use the middle. And in fact, if you use the middle voltage, I might actually accept that as an answer. So what did you get for the resistance?
Yeah, that's what I'm going to ask. Can you show me how to find the resistance? Because I think the parameter resistance, again,
hang on. The
time.
No, actually you can't find the resistance. That's another problem because you don't know how long it takes to discharge the capacitor.
5 time constant.
Yeah, and what's the time constant? Do you know the time constant?
No, but I know 5 time constant is 0.03.
No, you don't know that because the capacitor hasn't fully discharged at that point. It's still discharging.
Oh.
Yeah. But actually, interestingly, we could use this approach to work out the resistance. This is something we don't know. This is something we know, kind of. And this is the power which we just worked out. What is the power? 65.3. And what is the average voltage? What's the voltage at the beginning? It's a 3, isn't it?
Mm-hmm.
And at the end?
0.4.
0.4 at the end. Okay. So, the best we can do is work out the resistance from using this formula, but I don't think we could use this formula to get the power, although we could use it to get the resistance, or at least an estimate for it. The reason I say it's an estimate is because I'm not really happy about doing this because the graph is not a straight line, so the average is in the middle. But it'll be close, so it'll do. Anything else? By the way, Lee, how different was your answer for power?
Mine is 600.
10 times different.
Yeah.
It's quite different. Okay. Right, what's the next question in that paper that's